We're going to introduce nuclear chemistry today. You're going to see the difference between chemical reactions and the nuclear reaction that you saw in your do now. Today we'll talk about 3 types of radioactive particles, alpha, beta, and gamma, and you will learn how to write and balance nuclear equations today. We'll get into nuclear decay rates next week. This chapter is critically important. It's part of the honors curriculum. It's no longer part of AP, so you wouldn't see it there. But you might need it for college chem, and many of you will go on to take SAT 2 chem where it will be assessed. So it's a good idea to introduce it in honors, and it is extremely easy and you will be successful with it. What we're looking at here first in terms of nuclear chem is nuclear radiation. We know from what we talked about earlier in the year is that some isotopes are radioactive. What is an isotope? What is it? What is it? Uh-oh. What is it? What is it? You have a different number of neutrons. Is it the same element? Yes, it is. So, for example, you can have carbon-12 and carbon-14. And those are isotopes, atoms of the same element. You have the same atomic number, but different mass numbers due to different number of neutrons. In contrast, these 2 species are not isotopes. They are actually called isobars. You don't have atoms of the same element, and therefore they're not isotopes. So isotopes are atoms of the same element with different mass numbers due to a different number of neutrons. What do you use carbon-14 for? It's for carbon dating. You are right. And this is a radioisotope. And when you have a radioisotope or a radioactive isotope, this particular atom has an unstable nucleus that breaks down. And when it breaks down, it releases radiation. And as a result, you have a radioisotope. And I think for right now, with all the potential nuclear warfare that may go on, I think an understanding of nuclear chemistry is particularly important. So the branch of chemistry concerned with the structure of the nucleus of the atom and any changes that the atom's nucleus undergoes is referred to as nuclear chemistry. There are a lot of key differences between chemical reactions and nuclear reactions. For example, from the do now, this is a nuclear reaction. As opposed to a chemical reaction that you would have seen previously. For example, potassium reacts with magnesium chlorate to generate potassium chlorate and magnesium. And you know how to write and balance chemical equations at this stage of the game. So this is a chemical reaction, and you'll note that there are some key differences. You've got magnesium chlorate here, an ionic compound. You break those ionic bonds and you can form a new ionic compound. So this is going to happen when bonds are broken and formed. In contrast with a nuclear reaction, the nucleus is going to emit particles and or rays. So we'll take a look at some of those radioactive particles. What you will also see in a chemical reaction is you have the same atom on both sides of the equation as well as the same number, whereas in a nuclear reaction you generate a new substance. You don't have the same atomic number, yet it's a nuclear reaction. With chemical reactions, remember, we learned how to write chemical formulas based on valence electrons. You know, for example, that magnesium has 2 valence electrons, which it will lose to form a magnesium 2 ion. So with chemical reactions, you're dealing with valence electrons. With nuclear reactions, you can be dealing with protons, neutrons, or electrons. Also, and we'll talk more about the next two pieces later in the year, if you have a chemical reaction, for example, let's say you've got decomposition of potassium chlorate to generate potassium chloride and oxygen gas. This requires it requires an input of energy. It's not going to be huge. But in order for this reaction to go, you will need energy being absorbed. This will be an endothermic reaction. And this quantity of energy is typically not very large. In contrast, when you have a nuclear reaction, you will see a lot of energy being typically released. So there are differences in the amount of energy change that you would see. In a chemical reaction, it's going to be relatively low. In a nuclear reaction, it's going to be much higher. And in a chemical reaction, remember, it can be endothermic, or you could have an exothermic reaction, for example, with combustion. So here you'd have the energy term here. Relatively small changes in energy in chemical reactions, very large in nuclear. Another thing you can consider is we did a lab the other day where we had sodium bicarbonate and we reacted it with hydrochloric acid. We generated sodium chloride, water, and carbon dioxide, and we heated this reaction in order to speed up the rate of the reaction, so that designates heat. And temperature is one factor that affects the rate of a chemical reaction. We'll talk more about the factors that affect reaction rate, but temperature is one, pressure, concentration, and whether you have a catalyst present would be other factors. Whereas in nuclear reactions, those factors don't play a role. So there are some key differences between chemical reactions and the nuclear reactions we're going to introduce here. Just a very brief overview in regard to how radioactivity was discovered. The earliest discovery came prior to the 1900s. It's in 1895. Rowitschin actually found that invisible rays were emitted when electrons bombarded the surface of certain types of material. And these rays were discovered because the photographic plates would darken, and this led to the very first X-rays. So the invisible high energy emissions are actually X-rays. And if you go back and look at some of the earliest X-rays, this is actually an X-ray of his wife's hand. That is her ring right there. So the hand's upside down, the fingers are here. And these are the earliest X-rays. And we know that X-rays have greatly revolutionized medicine. Way back when, I don't think X-rays were used very much for medicine, and I'm just trying to do the math. My grandpa was born in 1908, which is a very long time ago, and when he was about 8 years old, so that would be 1916, he fell out of a tree house, and his leg was extremely deformed from the break. When he fell out of the treehouse, he fell on his leg, and he definitely broke his leg. But I don't think it was a compound fracture because the bone would have been exposed, but it was broken badly. And I know when they took him to the doctor, they wanted to amputate his leg, and his mom picked him up and said, "I'll see you later," and she took him home. But from that point on, his leg formed funny, And he always walked with a limp, and as he got older, he needed a brace, but he was way too stubborn or proud to sit in a wheelchair, so he wouldn't do that. But in any event, I guess they didn't have the x-rays back then, certainly that they had when I was a kid and that you see now. X-rays also are very helpful in determining somebody's age, not just in regard to when they do autopsies, but also even now some kids are developing faster than they should, and at 8 or 9 years old they're very tall, and doctors start to wonder if they're going through early puberty. And so what they will typically do is they will send the child to get an x-ray of their hand, and they're looking to see whether the growth plates have fused. Fusion of growth plates indicates that there's not much growth left. So a child could be 9, but their bone age could be that of a 13 or 14-year-old girl, say, and maybe they're not going to have very much more growth anymore. So it has greatly revolutionized medicine in many different regards. I'm sure many of you have broken bones by this point and have had x-rays. We have x-rays done on our teeth when we go to the dentist to look for cavities and things like that. But this is one of the earliest x-rays that was done. After Roentgen discovered the x-ray, a French physicist by the name of Becquerel was studying minerals that emit light after they had been exposed to sunlight, and this phenomenon is known as phosphorescence. And what he found is shown here. This is a photographic plate made by Becquerel. It shows the exposure to radioactivity. There's a metal Maltese cross here, and you can see that because around it is where the uranium salt left its mark on that particular photographic plate. And this led to quite a bit of types of radioactivity to photograph certain substances. And you can see it here as well. And then Marie Curie and her husband Pierre. Some of the kids said you learned a little bit about them in ACE International last year. Yes, yes, no, no? Maybe? Okay. What did you learn? Do you remember?
She discovered uranium, and then her husband got run over, and then she died of cancer.
There you go. See, you do remember. She took Becquerel's mineral sample, which is known as pitchblende, and she was able to isolate the components emitting X-rays, and this led to the discovery of 2 elements on the periodic table, radium and polonium. They were awarded with the Nobel Prize for their work and their discoveries, and they are credited with the discovery of radioactivity. She said that the process by which materials give off such rays is known as radioactivity, and the rays and particles emitted by a radioactive source is known as radiation, and they are credited with it. We're going to look at 3 main types of radiation. We've already talked about isotopes and radioisotopes. Remember that radioisotopes have unstable nuclei and they will emit radiation. And you will see that the unstable nuclei essentially emit this radiation to achieve a more stable configuration. We'll talk about that at the very end. The process is known as radioactive decay. There are 3 common types of radiation, and they are alpha, note the designation, beta, and gamma. Alpha particles are helium nuclei. Beta particles are fast-moving electrons. And gamma particles, very high energy electromagnetic radiation, are photons. The charge is determined from the atomic number because that's equal to protons. So a helium nucleus, an alpha particle has a 2+ charge. Beta particles or electrons have a 1- charge. And gamma has no charge and no mass. So 0 mass. In terms of energy, this is a little bit difficult to translate because 1 megavolt is 1.6 × 10⁻13 joules. But if you understand its ability to move through substances, then you'll understand its energy. And alpha particles are blocked by a sheet of paper, so they don't have the ability to move through substances easily. Beta particles are blocked by metal foil, and then gamma particles are not completely blocked by lead or concrete, so clearly they can move through substances much more easily. These have the highest energy, the gamma particles. Alpha particles have the lowest energy, and you can see that based on what they have the ability to move through. It was Ernest Rutherford who identified alpha, beta, and gamma radiation, and we talked about Rutherford earlier in the year. What else did Rutherford discover?
Protons, gold foil, electrons.
He did the gold foil experiment, which showed what?
Oh, it's electrons, neutrons, protons.
It showed that protons were located in the nucleus of the atom. Remember with the gold foil experiment, Rutherford showed that the atom is mostly empty space, but there is a dense nuclear core where the protons are located. Later on, Irene Curie, who is the daughter of Marie Curie, along with James Chadwick, showed that the nucleus also contains neutral particles known as neutrons. His experiment is shown here. It's all written out, so I'll just walk through the diagram with you. You have a radioactive source passing it through a small slit, and then you want to look at these particles. You want to see if they're charged particles. So you have a positive plate and a negative plate. And you will note that the beta particle moves toward the positive plate away from the negative plate. So you can conclude that the beta particle has what? A positive or a negative charge? Definitely a negative charge because it moves toward the positive plate. On the flip side, the alpha particles move toward the negative plate, so they have what type of charge? Positive. The gamma rays go straight through. They're not deflected in either manner, so they have no charge. They're neutral. Also of interest is the beta particles are deflected more than the alpha particles. So if you compare their mass, think about a beach ball at the beach and it's very windy and you're smacking it around. Does it move around a lot or does it keep its path? Moves around a lot, whereas a soccer ball is going to keep its path. So the lighter it is, the more it's deflected. And this also showed the beta particle must be of lower mass than the alpha particle. We're going to talk about these three different particles. You're going to learn how to write balanced nuclear equations. I promise it's really very, very simple. It's baby math, just addition and subtraction. But just as a review, 5 minus 3 is? 2. 5 minus negative 3 is? 8. Let's try some more. 4 minus negative 1? 5. All right. 6 minus negative 2? 6 minus 2? 4. All right. So that's the kind of math you're going to need. I think you're ready.
Negative makes it positive.
Yes, because a negative, subtracting a negative, that negative jumps it and makes a positive, right? Is that how you learned it when you were little?
I'm learning right now.
Did you learn it like this? This is how we were taught 100 years ago.
Well, when I was taught, it's like a 3.
It jumps and turns.
We learned
I
change.
Yeah,
No. That's with that's like with fractions, right?
Well, no, you change split.
Yeah.
Well, no, if you have like a 3 and a negative 4, you just make both the subtraction and the negative turn into a plus.
All right. So we're going to talk a little bit about alpha, beta, and gamma. Very, very, very easy. You'll be masters in about 5 minutes. An alpha particle, abbreviated as such, is a helium nucleus. Charge is 2+ because you have 2 protons as we discussed. I'm going to show you how to write a balanced nuclear equation for this type of emission. It's all written out for you there. I'm going to show you a very simple way to go. It says radium-226 emits 1 alpha particle. You will need a periodic table to do this because you're going to be often working in the F block, which you're not going to be that familiar with. We've got radium-226. That's all they gave us so far. And it emits an alpha particle. An alpha particle is a helium nucleus. The way I write a balanced nuclear equation is I make sure the superscripts on both sides of the equation are equal. I make sure the subscripts on both sides of the equation are equal. Keep in mind a sub is under, like a submarine, so that's a subscript. The way I go about this is I use my periodic table and I get the atomic number of radium. It doesn't matter if the mass number matches. It doesn't have to because you can have isotopes. The atomic number is unique. It identifies a substance. What plus 2 is 88? What plus 4 is equal to 226?
222.
I use atomic number of 86, periodic table, and I see that this is radon, and that's a balanced nuclear equation showing alpha particle emission.
Question, is this all we do? Because if it is, I could pass that place for once.
We say it's radon.
This is radon. All right, so this is balanced. You can see the subscripts are equal. 86 plus 2 is 88. 222 plus 4 is 226. You will also see that the atomic number and the mass number decrease when you have alpha particle emission, giving rise to a new substance. Let's take a look at a few others. The next example, labeled A, says thorium-232. Remember, the number after that dash is the mass number, and it's going to emit an alpha particle. What should I do? Ooh, what?
There's something plus 2.
Well, you have to figure out what this is, right? How do you get that?
It's 90.
Periodic table, it's 90 is correct. What plus 2 is 90?
88.
Or you can do 90 minus 2, whatever rocks your world. 232 minus 4 is?
220.
Use your periodic table, and this is radium. Let's do another one, and you're going to get a ton of practice on this.
It seems pretty good.
It's pretty easy. Nobelium-259 releases 3 alpha particles. We've got to go after this atomic number. What is it?
Is it always going to be the helium?
Oh, 102.
If it's an alpha particle, it's the helium.
Okay.
So what is the atomic number of nobelium?
102.
102 is correct. Now just be careful with the math here. 3 times 2 is? And 3 times 4 is? So 102 minus 6 is? And 259 minus 12 is? How do we get the substance? What do you use though? Use the 96, right? And this is curium, named for Marie and Pierre Curie. Piece of cake so far, right? An alpha particle is a helium nucleus. Questions so far? Easy, easy? Alrighty. Another type of particle is a beta particle. And a beta particle, as we said, is a very fast emitting electron. It is emitted from a neutron of an unstable nucleus. A beta particle has this designation. It has insignificant mass, hence 0, and a 1 minus charge. Let's take a look at the example. It says I-131 releases 1 beta particle. Process it grossly similar. This is going to be my beta particle. And again, you have an equation. Make sure you're adding the things on this side of the equation. Iodine has an atomic number of 53. And just be careful of your math here. What plus -1 is 53?
54.
54 is correct. No change in the mass number. 54 is the atomic number that identifies element xenon. So this is a beta particle. And you can see here that with beta particle emission, the atomic number increases, the mass number remains the same. As we said earlier, beta particles are essentially high, very quick moving electrons. They have decent penetrating power. They can go through a thin sheet of metal foil. Go ahead.
So when there's a beta particle, it essentially results in isobars?
Yep. If you have 1 beta particle, yes. If you have 2, then no.
Okay.
I take that back. No. Yes, a beta particle will always result in an isobar. Yes, you are correct. Yes, yes, yes. Very good. All right. Let's take a look at these 4 examples. We'll do 2 together, and you can do 2 on your own. The first one says thorium-232 releases a beta. Thorium has an atomic number of 9. Just be careful here. What plus -1 is 90?
91.
Good. Don't mess up that baby math there. And atomic number 91, protactinium. You can make it a little trickier. You have uranium-235 releasing 2 beta particles. Periodic table to get the atomic number of uranium. What plus -2 is 92?
94.
Mass number change?
Yes.
No,
What?
because 2 times 0 is 0. Identity property of multiplication. And you are correct in that regard because you do have an isobar. That was an excellent finding. And this generates plutonium. Back to the future, plutonium. I would like you to try C and D. See if you can put the alpha and beta. Well, you want to do one more together?
No.
All right. So you try C and D. See if you can do it. I'll do it too. Hello. We're filming. Careful, careful. Thank you. What do you want? Oh. I'll have to. I have to come down with that. I don't have it right now. Okay.
Sorry, you're recording last night.
Be careful with D. Ready?
Almost.
Let's see what you got. Yes?
If the mass number on that periodic table of elements isn't exact.
You could have an isotope here, so the mass number doesn't have to match. You just grab the atomic number to get the element. Careful. And you'll see an easy one like this on your next quiz.
Yes, I use curium instead of curium.
What's the matter?
I got confused when it said there's one alpha and one beta. So you put them both in there?
Yeah, that's like one boy and one girl sitting on the sofa. You put one of each on the sofa.
What's that supposed to mean?
No, I'm just giving an example. You can't put, you just do one of each. So if you have one of each,
That's disgusting.
if you have one of each,
I sit on the couch.
you have one and one.
That's a sofa.
And then if you have more than one, you need to indicate that with what's equivalent to a coefficient. Alrighty? You're going to get a ton of practice. Question? You want to do another one? All right. I'm just going to make one up. Let's say that we have berkelium 100. And it's going to emit 2 alpha and 1 beta. So the first thing I do is get, this should have been, actually let's change that up a little. Let's make it more realistic. Let's say we had 250. I use my periodic table and I get the atomic number here. 2 times 2 is 4. 4 plus -1 is 3. 2 times 4 is 8. Are you with me so far?
Yeah.
All right. So what plus 3 is 97?
94.
And 250 minus 8 is?
242.
And how do we figure out the element?
You look at the periodic table.
Does it matter if the mass number matches?
No.
Why don't you multiply the 8 times the 0?
No, this is plus, so it's 8 plus 0 is 8.
Oh.
And then this is 4, and 4 plus -1 is 3. So 3 plus 94 is 97, and 8 plus 242 is 250. Does that make more sense? Alrighty. So that's beta. Now sometimes in these reactions you'll also have a gamma particle. But it doesn't affect what you generate. Let's say that you had 2 gammas. When you see gammas in there, it doesn't affect what gets generated. It just indicates that a lot of energy is going to be released. So this is a gamma.
So gamma does not very much.
Gamma is not going to affect what gets generated here.
It just tells you energy being
A lot of energy being released. Yep.
Is it always going to be plus?
Yep.
Right.
And that last piece, another example is given right here. So gamma. Those are high energy, short wavelength, but doesn't change the atomic number or mass number. It just means that a lot of energy is released. Alrighty, one more piece of the puzzle so that some of this makes sense, because we want to know why certain elements release beta or alpha and or gamma. Some of them actually emit what's known as a positron, and some of them capture electrons, and we'll talk about why that occurs. So it turns out that only 17% of isotopes are stable. And when you're talking about particles in the nucleus, such as protons and neutrons, they are known as nucleons. Protons have what charge? Positive. And neutrons are?
Neutral.
So you are shoving a whole bunch of positives in a very small space in the nucleus. So in order to counteract that type of repulsion, you need neutrons there, and there is a strong nuclear force that acts on subatomic particles that are so close together, for an example in the nucleus, and that's what keeps protons in the nucleus rather than just popping out. And we're going to talk about that nuclear force and how you know if the nucleus is stable. You can correlate the stability of the nucleus with its neutron to proton ratio. This is very, very simple math. We find that atoms that have low atomic numbers, that is less than or equal to 20, are going to have very stable nuclei, and that's because their neutron to proton ratio is 1 to 1. For example, we can look at helium. We can look at carbon. We can look at calcium. All of these have atomic numbers of 20 or less than 20. Proton is always equal to the atomic number. How do we get neutrons?
Subtract it from the amount.
We just subtract it, right? A neutron to proton ratio in this case would be 2 neutrons to 2 protons, or you can write 2 neutrons to 2 protons. And when you divide it, I'm going to maintain the 100th place here. You'll see why in a few minutes. You get 1.00 to 1 for the N to P ratio. Similarly here, we have 6 neutrons when we subtract, 6 protons. 6 neutrons over 6 protons is also 1 to 1 ratio. If we subtract, we get 20 neutrons to 20 protons, neutrons over protons, and that too is a 1 to 1 ratio. Elements with atomic numbers of 20 or less typically have about a 1 to 1 ratio. That confers nuclear stability. Now let's consider, for example, we've got gallium, and as we go across that period, we've got bromine, what has happened to the number of protons here? Has it increased or decreased? And what about neutrons? It has increased as well. As you increase protons, you need more and more neutrons so that those protons don't repel each other that much. And that leads to a strong nuclear force. But as you have more and more neutrons, your neutron to proton ratio is going to increase more than a 1 to 1. It can go all the way up to 1.5 to 1, but when it gets higher than 1.5 to 1, you are outside a band of nuclear stability, and this is where radioactive decay will occur. For example, if you have lead 207 how many protons?
82. No.
Yes.
Yeah. 82. Yeah.
And how many neutrons? And now if you want the neutron to proton ratio, you have 125 to 82, and you have 1.52 to 1, and that's my neutron to proton ratio. You can see that this ratio has increased greatly compared to what we had previously. When the ratio is greater than 1.50 to 1, you are outside the band of stability, and we're going to take a look at that and what happens.
How'd you get that one? When it's 1.52 to 1?
Well, you basically just divide it by itself for the second one, right? So this one is this over this, and this is just this over itself. If you look at this graphically, you've got neutrons here, you've got protons here. So helium is here, calcium would be here. That's the 1-to-1 ratio. You can go up to 1.5, so within this band, you've got stability. Below the band, you don't have stability. Above the band, you have stability. So if we went back and looked, for example, at let's go back to this one right here. So thorium's neutron to proton ratio, how would we get thorium's neutron to proton ratio? 90 protons, how many neutrons? How would we figure that out? 142, and we would divide that by 90, and we have 1.58 to 1. Inside or outside the band of stability? Outside. And then 228 minus 88 for neutrons divided by 88. Actually, that didn't work. Why not? Let's try this one. I know why it didn't work. 259 minus 102 is 157 divided by 102, and that is 1.54. This one, 247 minus 96, that's 151 divided by 96, and that didn't work either. So what happened there? Did it get more stable or less stable? Less stable. And we'll take a look in a minute at one that gets more stable. So as we said, your band of stability is on that graph within that region, and you will have stable nuclei. Below or above, you will not. The band of stability ends with bismuth 209, and that's why all elements with atomic numbers greater than 83 are radioactive. The type of radioactive decay that occurs depends on the causes for instability. If it's above the band, they generally have too many neutrons, and so you need a way to decrease neutrons. Beta emission typically will decrease that neutron to proton ratio, and that will get you back in the band. However, if it is lying below the band of stability, there are two common types of radioactive decay that can occur, and these will be new: positron emission and electron capture. a positron can be emitted, and it looks as follows. How does the positron differ from the beta particle?
The one on the bottom is positive.
The one on the bottom is positive. So if you look at carbon 11 emitting a positron, here's carbon 11, here's your positron. What happened to the number of protons? It decreased. Another type that you can have is electron capture. An electron can be captured. If you capture something, you grab it, and this is going to be on the left side of the equation here. What happens to the atomic number now? It decreases, and you'll see that that will up the neutron to proton ratio. Let's do a few examples of those. There's a whole bunch here that I'll give you an opportunity to do. I want to look at 4 and 5. Let's start with 4 and 5. On number 4, it says calculate the neutron to proton ratio for thorium-234. Is the ratio inside the band of stability? You try that one, you can do it. The band of stability is between 1 to 1 and 1.5 to 1. What'd you get? What'd you get?
No.
What was your ratio?
1.6 to 1.
That's what I got. Now look at number 5. Try and do 5. It says write a balanced nuclear equation for the beta decay of uranium-235. What'd you get? What'd you get?
1.55 to 1.
So the neutron to proton ratio decreases because 1.53 is less than 1.55, right? And so if it continued to emit beta particles, you would expect that the neutron to proton ratio would decrease more and more until it was within the band of stability. So with beta emission, you will get a decrease in the neutron to proton ratio. Yep.
Would it be? It says -1. How should I add it? So would it be 91 or no?
93 plus -1 is 92. sugar. Right. All right, let's look at, I want to look at 7. Just in terms of writing the equation. I'll do all of these out for you so you have it. But let's look at 7. On 7, it says nitrogen 13 captures an electron. So if you capture the electron, it's on the left side of the equation. 13 plus 0 is 13. And 7 plus -1 is 6. So what do you generate? Carbon. The rest of it you'll be able to do. Let's look at 8. I want to make sure you're comfortable with these different ones. It says lithium 5 emits a positron. How do we make a positron? +1, right? Looks like a beta particle, but it has a +1. So what would you make? What +1 is 3?
1 plus 1 equals 3. It's going to be 2.
And does the mass number change?
No.
And what element is that?
Helium.
Positron emission, electron capture. When you capture, it goes on the left side. When you emit, it goes on the right side. Positron looks like a beta particle, but it's got +1. This is a positron. Sounds like a silly book that you're reading.
So positron is a beta particle.
But it has a +1. The other problems I think you can do, and when you work through those, I think you'll feel very comfortable. I'll write the answers out to those here so you have them. I'm going to give you classwork 3X, because sometimes I put it in different places throughout the year. I think it fits well right here. You can do 1 through 7. And you can do 10 through 15. And hopefully you'll have a solid understanding of alpha, beta, gamma, positron, electron capture, and just an understanding of the discovery of radioactivity. I also want to reiterate that this will not be on your STOIC test next week. It will be on your next quiz, but I usually just put 2 easy questions, and I think those questions would come right from these 8 examples and problems that I asked you to do. So I would have those done for Monday. I'd have the classwork done for Monday. You can pick up the classwork once your lab is done. Questions in regard to nuclear chem?
I would like to subscribe. Smash that